Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. I hit record. Chris, I hit the button.
Well, hold on. I'm still tapping.
Still tapping.
Okay,
you're tippity tapping around, moving all over your NASA panels there, getting your stuff aligned. You know what, Chris? I must say,
what?
I'm going to give you a compliment, so get ready. They don't come very frequently.
They don't come very often.
If at all.
I'm just your sidekick.
Sidekicks don't deserve compliments. You've been pretty techno-savvy recently. We haven't had many major hiccups out of you recently. I'm proud of you, man.
Get this. So I got an email from our technology person at the high school today, or yesterday anyway. He said, I have 3 brand new computers to give away, and I chose you because I know that you'll use the technology and blah, 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 blah. And I'm like,
that's nice.
Jesse would be so proud.
I would be. That warms my heart. That warms me heart. We've trained you up well over here at Planet Geo, Chris, with all the technology.
But you know that all that comes with a new computer, it's been a time drain today.
Oh,
if you know what I mean, like setting up a new machine and getting logged into everything again, and
admin privileges and all this nonsense. I mean, yeah,
yeah.
Oh goodness.
Oh yeah.
Well, you got your NASA set up now, so you're ready to rock with Planet Geo here. Pun intended.
Oh, it was okay. Nice.
It was. So, Chris, this episode here, I'm excited about this. I know you are a cave guy. You're a cave dweller. You like caves, right?
I do. I like caves, but I'm not a cave dweller. I don't know how to take that comment.
Yeah. I had to get
I'm not
that
sure
one
I
in there.
like that. I'm a cave dweller. Would you think Jenny would like it if I said, "Hey, Jenny, Jesse just called you a cave dweller"? You think
she's
like
not.
that?
Jenny's a daughter of the light and the rainbows and the butterflies. You, my friend, are a slug cave dweller, I think.
All right.
You
in
your little recording booth downstairs, in your little man cave recording booth you got. I mean, it's pretty good.
I know. I like this place though. Yeah. I've got it just how I want it.
Exactly.
Yeah, I do like caves. You know what I like though, Jesse, is I like to learn the intricacies of how each cave works. They're so different. You know, you talk about like the formation of, we're going to mention today Jewel Cave and in the Black Hills and Wind Cave. I think Wind Cave has such a really cool story.
Let me interrupt you real quick, Chris. Which one did we go on when I was a student on the summer science trip with you? Because I know you've switched these around, and I have. My dad led that trip, so like I went as a kid on that trip previously, and I think we might have gone to one or the other. So which one did I go on with you as a student?
I think Wind Cave, but I'm not sure. We've also gone to Jewel. They have just really different things to offer. The cave, when you get in it and you get into the nitty gritty of it, it's just really, really different. They're very close together. It's just astounding that their stories are so different. They're geologic stories. And so that's what I love about it. And, you know, everybody thinks that Mammoth Cave, this is what we're doing. This is our first episode of a series on Mammoth Cave and the geologic story of it. People think it's simple. And you and I know this is really not a simple story. There's a lot going on for Mammoth Cave.
Okay, a comment and then a question. Mammoth Cave is, well, here's what I like about caves. And I don't really like caves. I mean, I don't hate being in them.
Oh, you don't like yeah.
But there's like bits of claustrophobia. Or there's something about it that is physically uncomfortable to me. The geology is amazing. You get to see rocks in place. You get to see the inside of the earth in a cave. That's pretty cool. And what I like about caves is when you're standing in the rocks, it's basically like geology's kind of fractal. You see it at all the scales. You see a big tunnel, and then you see all the hydrothermal features, and there's just so many scales of stuff happening, from really minuscule tiny microbes to like huge tectonic reasons why the cave is there. So that's what I think is really interesting about caves. So Chris, sorry, that was a long comment, but now to my question here, because I went to Mammoth Cave on an undergrad field trip. Actually, it was one of the times I've been to Mammoth Cave. What's your personal connection to Mammoth Cave?
Same thing, almost exactly the same thing. I don't know. You know this about me. I love it when the story comes together, when you learn about the formation of something. And so when you're walking around the area, when you're driving through this, and it's a huge area, right?
Yeah.
And then you get into the cave, and and you know something about it. I love that aspect of it. And so that was one of my like early field experiences actually.
Oh, really? At Grand Valley?
Where that clicked, you know? And I was like, oh my gosh.
So another quick question for you. In your experience or your opinion, is this a pretty common field trip for schools in the Midwest to do, to drive down and go to Mammoth Cave? Because, you know, in Michigan, there's not many outcrops, and I don't know what the drive is, but I seem to remember like, you know, 6, 7, 8 hours, something like that from Michigan.
Yeah.
I could be way off.
That's
but
about right.
About right? Okay. I feel like this might be a pretty common weekend field trip for, let's say, geology majors to go on. Do you think that's true or no?
I would hope so. I mean, you went there with Hope. I went there with Grand Valley. I think they still do that. They do a trip down to Mammoth, and, you know, clubs do it too, like geology clubs through the universities. Did you have one at Hope? Did you have a geology club at Hope?
Yeah, I mean, but we didn't do too much separate stuff from classes because everybody's kind of taking the same classes at the same time through it, just the way the structure was set up. So
I'll tell you, I could put together a 4 or 5 day trip down to Kentucky, seriously, and we would do Mammoth Cave as one part of that and spend then a couple, 2-3 days in Red River Gorge and just tear it up. It would be amazing.
It's a great idea. Geology is so good, and it's, you know, it's close to a lot of stuff. So I feel like a lot of people have been to Mammoth Cave, even though it's not like one of the necessarily premier national parks or most popular ones. A lot of people have been there because it is kind of close to a lot of different stuff. So Chris, let me just set the stage here. So if you're listening to this in the podcast, this is part 1 of a probably end up 3-part series on Mammoth Cave National Park. If you're listening to this, the audiobook version of this with images is probably live on the Camp Geo app. So you can go there, you can listen to all 3 episodes with the images that you need integrated with the audiobook. You can download the first link in your show notes is the Camp Geo app. So head there. There's a bunch of free content and then some paid stuff as well, including the Mammoth Cave National Park. This is part 1, and we're going to intro kind of the overview. This episode chapter is going to be the overview geology, and then we're going to get more specific in 2 and 3.
That's right. We're going to get into, in part 2 and chapter 2, we're going to get into some of the specifics about Mammoth Cave geology, and then we're going to tie up the loose ends in the last episode, talking about the passage.
Yeah, this is the biggest cave, the longest known cave system, and there's a reason for it, and we're going to talk about the reason. Like, what is the, again, back to scales, what is the tectonic reason, the large scale reason why this is a huge cave compared to other ones all throughout the Appalachians and all over the place that are much smaller, right? We're going to cover that. If we're on Chris Bolhuis's trip and we're on the bus driving down and Chris has got the microphone up front, what are you saying on the way down to Mammoth if Mammoth is our first stop? What's your pitch?
Well, I don't know. We're going to go see the longest cave in the world. You know, that's kind of an impressive thing. Let's put some numbers to it. Mammoth Cave is over 675 kilometers long, or 420 miles. It is the longest cave in the world by far. It's not even a close call. The second longest cave is somewhere in Mexico, and it's 250 kilometers shorter. I take students to Jewel Cave and Wind Cave in the Black Hills. Those are 5 and 6 respectively in terms of their known lengths. There are some things that we don't know about them yet in terms of Wind Cave. There's a lot of it that hasn't been mapped yet, but that's where we're at right now. And so it's just, I don't know, the biggest on the planet. You're a big deal then, just by default.
Yeah, no, that's right. You're the biggest and maybe arguably the best because of that. And if you go into Mammoth Cave is called Mammoth Cave for a reason. It feels huge. There are rooms in there. There are passageways that are unbelievably big. You really can't imagine, at least I found it hard to comprehend how this could exist with stuff above us. This is so big, right? The scale inside is amazing. The details are not important. Find a map when you go to the National Park store that's detailed and shows you all this stuff. We just put this here because this is a huge cave network, importantly. Sorry, Chris,
that's right. That's no. That's my next point. You get the segue word because, you know, Mammoth Cave is this network of caves, and there are over 400 of them in this mapped area that we're pointing out in image number 1 here. So it's aptly named. Let's just say that. Calling this thing Mammoth Cave it lives up to its name for sure.
I mean, Chris, you're exactly right. This is a huge cave system. let's talk briefly about the type of cave, because there are different types of caves. And the types, what we mean is, how did it form? How did we get a cavern forming? This one was formed by water dissolving rock. And the rocks themselves are what we call Mississippian aged, which Mississippian is a time period. It's 355 to 300 million years ago. These are carbonate rocks, and we exist in what's called karst topography. And those two are intimately linked, and we'll talk about those in more detail later on. But this is a solution cave. And Chris, question, do you cover cave types in your college level geology class that you teach students? And if so, how do you lead it in, or maybe you don't?
I do, but I don't parse them out this way and say these are subcategories of caves. I talk about lava tubes. I think they're really important, in terms of how lava can spread laterally for these vast distances because it stays it's like in a thermos, when it's in a lava tube.
Let me say something real quick, Chris. I was going to be impressed if you taught your students the different cave types, because this is, this is deeper level stuff. This is like getting into upper level geology classes in college if you're covering kind of the cave types. But let me just give an overview of what this cave type thing means. It just means, what's the physical process by which you formed this underground hole, really, that is a cave. And you said lava tubes. That's a great one. Lava with that's flowing underground has crystalline rock above it, and it creates this tube. You can get ice caves as well. You can get aeolian caves, which are caves formed in sand dune type areas and sort of windblown things, and sea caves. I think sea caves are probably one of the most common, or the ones that people would think of. There's solution caves, which we're going to talk about, and sea caves, you just imagine the wave action is cutting a cave into a cliff. That's really what's going on.
Right. These are fairly common with the river systems in Kentucky, where you can go kayaking and you can go into these. They're not really sea caves, but they're caves in limestone right along running water. They're pretty spectacular. That's a really fun thing to do, actually. So, yeah, I don't get into all of that, in terms of caves. So sorry, I'm not all that impressive. Just,
hey, Chris, you're
just moderately impressive.
Just mostly very impressive, just not, fantastically impressive.
Yeah, right. That's right. Well, okay, so Jesse, let's transition into, because this episode is all about general, really limestone cave formation, right? Because that's the most common type. Any student or anybody that's ever taken an intro level geology class has had to identify the rock limestone, or they had to identify the mineral calcite. And I don't know, I'd be hard pressed to imagine going through a class without having the opportunity to drop some weak hydrochloric acid on a limestone or a calcite crystal and watch it effervesce and watch it fizz.
Totally.
It just shows the reactivity of limestone, which is calcium carbonate. You mentioned that earlier, in weak acid solutions. Caves, the vast majority of caves in the world involve the rock limestone,
and
like
Chris,
hands down.
This is a great place to start. If we were to list, and we have this on image number 2 in our stack, the ingredients, the recipe for a solution cave, if you're going to form a solution cave, which is formed by the dissolution, dissolving of rock, this is what you need. The 4 things. Number 1, by far, is suitable rocks. That's first and foremost. And if I gave...
Yeah.
I think any first week of class, my big lecture hall, 250 students in it, within the first week, if I said, gave them 5 rocks, picked a granite and a basalt and a metamorphic rock and a calcite crystal, and a quartz crystal, and said, which one is the easiest to break apart? They're probably going to pick the calcite crystal, right? You could pick it up and you can look at limestone and you can kind of just feel that this rock is going to be kind of easy to break down and dissolve, I think.
Ooh, Jesse, I love what you just said, because I've started doing this with my classes, is rock identification. Limestone can be a hard rock because, as we've said before many, many times, it's the Katy Perry of rocks. It has so many different looks to it.
You've said, Chris. I've never been quoted saying that, but you have.
All the time. My kids know it by heart now. But I say this, just shut your eyes, hold the rock in your hand. Don't you feel that it's soft? It's soft.
It has
it's
light.
That's right.
It's just There's something about it that you can feel, and you don't have to handle too many rocks to kind of realize this is not granite. Granite will be hard to dissolve. This rock, limestone, will be easier to dissolve. So number one, suitable rocks in our recipe.
As an example, just to contrast the reactivity of a suitable rock, another rock, sedimentary rock, that's closely related to limestone is dolostone, but it's far less reactive. In order to get this to effervesce, to fizz in acid, you have to like take a scissors and create a powder on top of the rock, create a lot more surface area, and then drop acid on it, and it'll fizz like a flat pop. So it's much less reactive. So caves, most often, here's the suitable rock. It's limestone, which is calcium carbonate.
And it can be dolostone. It can be marble. Marble's just metamorphosed limestone. So it's the same chemical constituents. Gypsum and halite, those are minerals also that are quite easy to dissolve if you have the second ingredient in the recipe, which is a solvent. Chris, what do we mean by solvent here?
Something to dissolve something else. That's what I think of when I think of a solvent. We're talking about slightly acidic groundwater is the solvent that's involved in this kind of cave formation.
It's the Chris Bullheis family chili recipe compared to your stomach lining, right?
That's right. You got that right. That's 100%.
The multiple award-winning Bullheis family chili recipe that it fights you when you eat it.
And we're going to come back and talk more about each of these in a little bit, but we're just kind of running down the 4 necessary ingredients. So we need a solvent. And then Jesse, the third one maybe is not as easy to imagine, and this is hydraulic gradient. So can you go ahead?
We've got an image for that. Let's save that for a minute. The last piece we need, which is intimately related to hydraulic gradient and really all chemical reactions, is time. We need time for these chemical reactions to kind of drive themselves forward. So we kind of already talked about in detail, number one, the suitable rock types, limestone, dolostone, marble, gypsum, halite. Why do we focus on limestone though, Chris?
Well, because it is very reactive, but like you said, it's not the most reactive. Gypsum and halite are more soluble than limestone for sure. But limestone is the most common sedimentary rock that exists at the surface of the earth. And so by default, then it's going to be the most important in terms of cave formation.
Right. That's right. Marble, there are places, Sequoia, Kings Canyon, Yosemite, that have marble around, and marble's not, you don't form this big extensive network of marble or big extensive layer of marble like you do in sedimentary sequences with a big package of limestone. So it's hard to make a big continuous network of caves in a rock type that's not a big continuous package of rocks.
And that's one of the shocking things when you go to Mammoth is the vertical extent. This vertical stack of rock, limestone, it's immense. It's impressive. You don't get that with rocks like marble or gypsum or halite. It's far less common, I should say.
That's exactly right. Exactly right.
Jesse, let's get into why is groundwater acidic? How is carbonic acid created? First of all,
how long
what
do we
is
have?
Carbonic acid? Well, we don't have long.
Okay.
We're keeping this, this is for everybody. This is for the families walking around, going to get into Mammoth Cave, and so they know what they're looking at and how it all happened. So, doctor, let's keep this
Let's keep it out of the weeds. Okay. Well, you and I have talked a lot about this, including in our Earth's Climate book, which is basically all about the carbon cycle for all intents and purposes. And groundwater acidity is intimately related to CO2 in the atmosphere. When you have CO2 in the atmosphere and you have water exposed to that, rainwater, groundwater, surface water, the CO2, some amount of CO2 is going to dissolve in the water as carbonic acid or bicarbonate ions. And so that creates acidity. Now, there's a bunch of different ways to create acidity in water, but that's one of the big ones. That's one of the most important ones. And it's intimately related to how carbon cycles throughout our Earth. And there's a couple different rates of cycling. There's a fast carbon cycle, slow carbon cycle, etc. All sorts of complicated and very important geochemistry is related to this. But I don't know, Chris, is that how you explain it to people as well?
Absolutely. I mean, everybody knows that carbon dioxide is a really important gas. It's talked about all the time because of its effect on the greenhouse effect and climate change. Carbon dioxide is in our atmosphere. It's in pretty small amounts, but it's there and it's important. But the way that I talk about this in terms of something that maybe I think everybody can relate to is a carbonated beverage. Let's say a bottle of Mountain Dew or a Diet Coke that you buy at the store. It's mostly water. It's got some other stuff in it, and then they carbonate it, and that carbon dioxide dissolves in the water, and so your pop is going to be acidic also. It's going to have carbonic acid. So that's how I kind of, relate this in terms of if you put carbon dioxide and water together, some of that carbon dioxide is going to dissolve in it, and it's going to create a weak acid. A weak carbonic acid.
And it's important, Chris, because that's all you need is a weak acid. If you took a geology class at some point, you're listening to this, and you remember dropping a little bit of HCl, hydrochloric acid, onto calcite or limestone or dolostone, that's not strong stuff, right? Like, I'm sure you got that on your fingers, and it wasn't very strong. Now, that dissolved it really quick because it's much stronger, much more acidic than the groundwater we're talking about. But all you need is a little bit of acidity, and then you need our fourth recipe ingredient is time. You have more time, even if it's weakly acidic groundwater. We have many hundreds of thousands or millions of years to do this. This reaction can progress forward over time, so you don't need really acidic stuff. That's kind of the only point, Chris. So, okay, we covered recipe ingredient number 2. Number 3 is hydraulic gradient.
Can I have a crack at this one?
Yeah, absolutely.
I want to crack at this one. Because one of the things that I do, I like to take I knock a little chunk of limestone off one of my rocks, and I put it in a little Dixie cup, little clear cup, and I pour Mountain Dew in it. And I just let it set, right? First and foremost, we weigh the limestone on a scale. So it's dry, and we weigh it, and then I just drop it in the cup and put some Mountain Dew on it is usually what I use. And the thing is that the Mountain Dew quickly becomes saturated with calcium carbonate. It can't hold a ton of it. So nothing really happens. I can let that sit for a couple weeks and it'll turn to this nasty gel or whatever. But what I need to do is I need to dump out the Mountain Dew every couple of days and put new stuff in. That way I can keep the reaction going. And this is how I think of hydraulic gradient.
Ooh, Chris, this is a great analogy for, I think, explaining why you need a hydraulic gradient to do this cave formation thing. So this is great. Sorry to interrupt.
No, that's okay. You interrupted me to compliment me.
You're moving back up to sort of exceptional specimen category here. So, very, very extremely impressive.
Really, what we're talking about with hydraulic gradient is a steeply inclined water table where water's going to flow through the rocks. And what happens when you get this is the same thing with my Mountain Dew effect. If I just have water standing there, not circulating through and moving and then getting replaced by fresh water behind it, the water gets saturated with calcium carbonate. It can't soak up any more limestone. So if you have this gradient is just the geology fancy word for slope, rise over run. If we have this steeper gradient, then we're constantly getting fresher, cleaner water in that can soak up like a sponge more of the limestone. It can dissolve more of it.
That's exactly right, Chris. And let me just build on that. Just 2 additional points that we should probably make here is, why do you need more fresh water, or more, not fresh water, but more new acidic water? Let's put it that way. Well, the reason is because when it dissolves ions, when it dissolves the rock, that neutralizes the acid. You said that earlier. So you need to bring in fresh stuff because you want to keep the reaction going forward. It's like the old, high school chemistry class, products and reactants. You drive the reaction this way or that way, depending on what you have more of, right? And so we want more of the reactants. We want more acidic groundwater flowing through there, which will drive this reaction faster and faster. The second point is, where do we get these hydraulic gradients, or why do they ever exist? I mean, I think this is not necessarily an intuitive thing, because people often think of lakes. When you think of groundwater, you kind of envision this lake where the surface is flat in a lake. It's not that way in the groundwater system. And the reason is because groundwater percolates through. It takes the groundwater time to percolate from the surface down. So when rain hits the surface, it percolates down in. There is slope to the groundwater table. It kind of
Where's
follows,
the water going to?
Yeah,
right?
it kind of follows topography, right? So if you're up on a mountain and you drill down beneath your feet, you might have to go down 100 feet to get to a groundwater table to hit groundwater. But if you're down by the river bottom, in the river bottom, that's a key to this puzzle. If you go down to the river bottom and you're near the river, you might have to drill down 2 feet to hit groundwater, right? Why is that? Well, it's because the groundwater is flowing down to the river. The river place is usually where the groundwater level hits the surface, intersects the surface. And so basically the groundwater follows topography a bit. It's close to topography at least.
That's right.
If that
and
makes
then
sense.
Also, just to reiterate that what you're saying is that rivers, especially in this case in the formation of Mammoth Cave, rivers are fed by groundwater. So the groundwater's percolating through this calcium carbonate, this limestone rock, and it's making its way downslope, downhill to the river. And so because that river has incised so deeply, we have a fairly steep slope. And so we have water that's moving through and then getting replaced by fresh water, which keeps it able to dissolve these openings.
That's exactly right. And image number 3, Chris, shows a hydraulic gradient, what's called a hydraulic gradient. It just shows, you can see there's some topography to this. There's a hill there. There's wells drilled into this. And you can see up high, the height of the water in the well is going to come close to the surface, maybe just above it. Whereas when you're down further, the water is going to come up a lot higher because there's more sort of hydraulic pressure there. But that groundwater is following, that groundwater table there kind of broadly follows the topography. It's a little bit more subdued version of the shape of the land surface, but it broadly follows that. So water is going to be flowing downhill in the ground there, and you're going to be bringing fresh water or new acidic water from up high through the rocks down as it goes out. Down to the right is where a river would be in this image here.
And then the last ingredient, Jesse, we talked about it, time. And there's not really a lot that we need to say about time to add to what we've already said. The bottom line is these rocks are old. We hit it right at the outset. These are Mississippian age rocks. These are rocks that were deposited 350 to roughly 300 million years ago. The rocks are old. The caves are relatively young. Just to put a number on this, the cave formation began about 10 million years ago. But I think 3 and 4, hydraulic gradient and time, they go hand in hand. You have to have water circulating through the rock, but we also do need geologic time because limestone is soluble, but it's not that soluble.
Yeah. And Chris, let me just say, we need time. We need to have a long time that all 3 previous ingredients are together there, because there's a lot of different ways to change the ingredient structure. You can remove the solvent if the land surface raises up and the groundwater table drops, and then there's no more solvent in contact with your rocks. If you deposit some new rocks or change the tectonics, you kind of remove those rocks or metamorphose those rocks, you're going to destroy the cave and remove one part of the recipe for cave formation. So you got to have kind of a long, stable paleo-environmental condition here that allows water to circulate for, like you said, 10 million years in this instance to form something massive like Mammoth Cave formation. Okay, so that's the 4 pieces for this type of cave to form. Chris, the last thing we should cover here in this sort of really high-level intro into Mammoth Cave is karst, what's called karst topography or karst regions. So man, karst is such a cool thing. It makes this crazy, beautiful landscape. You're karsty, aren't you?
I'm feeling karsty. Absolutely.
Absolutely. Yeah, you are.
We did a whole episode. I think we might have done 1 or 2 episodes on just karst in and of itself. I mean, it's worthy of that. So the bottom line is we need to talk about sinkholes before we can talk about karst. And if you have
hold
caves,
on, let me just say, Mammoth Cave is located, this whole region is a big karst region around Mammoth Cave. If you are driving, if you're close to Mammoth, you're driving through karst topography. Just let's leave it at that. You look around you, you're in karst terrain. We'll explain that. So sinkholes, sorry, Chris.
So we need to define what that is. So sinkholes are when you have caves near the surface. And then those caves, you have these big openings just below the surface. Well, collapse happens. And so the roof of the cave just collapses down in on itself, and it creates this sinkhole.
So, Chris, quick story real quick. We had last year at Penn State, where we live in karst topography up here in State College, we had a sinkhole open up right near a parking deck, right underneath one of the main parking decks on campus, and had to close down the parking deck. So they managed to repair it. It wasn't a massive one, but this happens. There's a grocery store that almost got swallowed. I mean, this was a decade ago, but big sinkhole opened up in the parking lot, and all of a sudden you're like, wait, we didn't know there's a sinkhole here. We don't know how big it is. You got to survey it. Like, these things are not infrequent in karst topography.
Yeah, there was a massive one that opened up within the last 3 years in the Black Hills, right in a developed area. It was a big deal out there.
Oh, interesting. Okay.
Just outside of Rapid City. So for sure, if you have caves near the surface, then you're going to have sinkholes that are a potential hazard. And they are actually, this is a natural geologic hazard. So that's what a sinkhole is when the roof of a cave collapses down in. It kind of leaves this big dimple on the surface, and then it can lead to things like disappearing streams, which are just awesome geologic features where you have this river that is flowing and then it dumps into the sinkhole and just disappears. And so
disappears into the groundwater, right? So you can kind of, in karst regions, you get the groundwater's coming in and out of the ground a lot faster than or a lot more frequently than in other types of topography, because there's sinkholes and there's stream channels that dump out onto the surface really quickly. So yeah, it's a very interesting landscape.
So if you have this potential for sinkholes, karst is when you have a whole region that is just full of sinkholes. So you have water flowing through the ground, it's creating caves, the roof collapses down in, and you get these sinkholes. When you have this whole myriad of sinkholes at the surface, we call that karst. And this then also shows how it progresses with depth. As water continues to percolate down through the limestone, it'll open then different caves at different levels, especially if the river continues to downcut and incise, which keeps that hydraulic gradient steep and allows for the dissolution of the limestone.
That's exactly right, Chris. And so this is going to become very important when we talk about the specifics of Mammoth Cave here. That last point that you made, the last frame in this GIF kind of shows you, I don't know, this resonates with me like driving around karst topography. This makes sense. You're driving around hills, there's rivers, there's caves, there's sinkholes, and the rocks beneath your feet are easily dissolved. And that's a really important constraint, or that's a really important recipe there. And so here in Pennsylvania, in State College area, we have limestone in the valleys, and the valleys are fundamentally there because the limestone's there, and the limestone in these humid regions in eastern North America where we get a lot of rain, they're easy to dissolve. And so they get dissolved and the valleys form, the hills are more resistant rocks. It all comes back to the same thing. Limestone's easily dissolved. You can make this karst topography.
I have a question for you then about your Pennsylvania area. Do you have a lot of disappearing streams there?
There are some. They're not as common as I think down in Kentucky and Tennessee area. We have caves, certainly. They're not as big, but there are certainly caves here. Yeah. I mean, the rocks are...
Can you think of
I can't think of an example. I mean, you do see some that are smaller, unnamed streams that are smaller, little tributary streams. The problem is that we're in the Ridge and Valley province, so all the limestones are tilted on their side in the Ridge and Valley province, so you don't get this long, flat-lying structure that you get out to the west of us there.
Okay, that makes sense. Because those are just disappearing streams, and then when they rise back up is just
We do get, Chris, a lot of groundwater seeps that feed the streams, though, so you can see often, especially in the winter, if you go in the stream, can be, sometimes ice covered, just a slight layer of ice, and you'll go see the little bubbling areas where the sand looks like the sand is boiling up, and it's just groundwater feeding into a little pocket, feeding into the stream. So we do get those features for sure. It's just a really beautiful landscape.
Well, Jesse, and then one final thing as we wrap this episode up on just general cave formation involving limestone is that these karsty areas, karsty is a word that Jesse and I use. It's not really something you'd see in geology
It's
books,
made up. It's a Chris
karsty.
Bullheisism, and Chris is feeling karsty when he's talking about caves.
That's right. Why not?
Why not?
But they do make fantastic aquifers too. So residential wells and things like this, because you have this really if you tap into the right place, then you can get free-flowing water beneath the surface. And so it's a very important aquifer.
It's a very important aquifer, and it's a very rapid aquifer, because in Michigan, when you talk about the aquifer, you're talking about kind of a sandy layer down in the ground. So the water is flowing through sand and mud. So it kind of takes a while. It's better at filtering out stuff. In State College, Pennsylvania, actually this happened a couple years ago. Karst groundwater it's quick flowing and therefore kind of easy to pollute. And there's this example, they put a highway in and they didn't deal with the pyrite that was in one of the shale layers, and so you generated sulfuric acid, and that ended up dumping in. It didn't end up contaminating anybody's wells, but there was a big concern because that groundwater goes really rapidly, gets dispersed throughout the groundwater system. So it's actually kind of easier to contaminate in some ways because it's a stream flowing underground rather than water percolating through rock or densely packed soil, which is, I think, an easy visual to kind of wrap your head around, right?
Especially when you look at it in the context of image number 4, I think that's pretty easy to visualize. What you said is easy to contaminate, but it's probably also easier to mitigate a pollution problem. If you can isolate the source of the pollution, then you can shut that off and it's going to clean itself out because it's going to make its way out of there relatively fast, as opposed to something like mine. My water may just move, a few centimeters per day.
You're exactly right. So quicker to pollute, quicker to clean up, or easier to clean up perhaps too. So, and again, because the water's moving much faster, and that goes back to our hydraulic gradient thing where we need to have a constant supply of water here to create this cave system. So, all right, Chris, I think, is that a pretty good wrap for the intro here to Mammoth Cave? We've covered a lot here. Cave formation, the recipes for solution caves, karst topography, which we've talked about before on the podcast, but we have to reintroduce with this cool image for the book here and for Mammoth Cave in particular.
I think we can wrap it up just by summing it up again. For this kind of cave formation, we need to have a suitable rock. We need limestone. We need to have a good solvent, carbonic acid, and groundwater is acidic, slightly acidic because of the carbon dioxide. We need a good hydraulic gradient to enable us to keep on dissolving the limestone, and we need time. We need geologic time.
Long time for the reaction to progress and build these massive, beautiful caverns in Mammoth Cave. Okay, hey, well, that's a wrap. This, again, is part 1. If you're listening on the podcast, you can go to the Camp Geo app. You can get full access to all the Mammoth Cave episodes. There's going to be about 3 of them with the images, these really cool, beautiful images and GIFs we've made to kind of really help visualize these topics. You can head there. That's one way to support us. You can also head over to planetgeocast.com. There's a support us link there, and you can learn more about us, see past episodes, get a little extra stuff. You can also follow us on all the social medias. We're at Planet Geocast, or send us an email, planetgeocast@gmail.com. We always love that.
Cheers.